session, no one group is responsible for the right answer. We collectively are responsible to come up with the correct answer. We'll let you leave with incorrect information if you don't ask questions. Yes. Why does he do that? Well, he knows that we're going to come back to this later on, so it's in your best interest to make sure that you understand what is being said as it is being said. All right, group 1A, if you could please go up to the front. All right, group 1, take it away for us, please.
Okay, so we had problem 1 and like A and B. So in our diagram, we have like the toy is not moving at part of point A at the top of the hill, and its height is 56 centimeters, and then the 0 point is at the bottom.
So for part A, you're supposed to use the formula EG equals mass times gravitational energy times height to find the sledder's gravitational energy at the top. So it told us that the toy sledder had a mass of 6.7 kilograms. We did 6.7 times 9.8 times, we converted our 56 centimeters to 0.56 meters, and we got 36.77 joules. What questions do you have? Lucy? Why would the hill be in the system if there's no friction? I guess you probably don't need it in the system. You just put it in the system because that's where you got your height from it. So,
Yeah, I had my h equals 0 point under the ground, so it was much lower than what you did. Would that be wrong?
no. It would just
You just have more gravity here, and then the more that you have here, let's say you had 6, then you'd have 1 each.
yeah, you just have more kinetic energy.
No, you'd have the same kinetic energy.
Or
you just
same,
have
but,
more
yeah.
gravitational.
So you have the same kinetic but more gravitational.
In the second, yeah.
You would have more, if you had the 6 blocks of gravitational, then you would still have, here you would have a block of gravitational too.
Thank you. All right, let's acknowledge your group. 3, 2, 1. We're going to pause right there because I want to talk about something. And I'll give you a hint. In my last class, there were only 2 people that wrote down this stuff. I was surprised. But hey, they're adultish and they can do whatever they want. So would you agree that the kinetic energy is equal to 1/2 mv squared? Is that an always statement?
Yes.
Okay. Would you agree that gravitational energy is equal to mass times gravity times height? Is that an always statement?
Yes.
Would you agree that for this situation, we said the kinetic energy at the bottom was equal to the gravitational energy at the top? Is that an always statement?
No.
No, that's a situational. We happen to set it up for this case and this case only. But if I said that the kinetic energy was equal to 1/2 mv squared is equal to mgh, as honor students, we should recognize what's on both sides of the equation.
Yeah.
And then what happens to it?
Cancel out.
It cancels out. The mass doesn't matter because, like this group eloquently told us, yes, it has more mass in the second part of the problem. So yes, it had more energy, but that same amount of energy shows up at the top, and it had more mass, so more mass for the more energy, it still went to the exact same height. I guarantee you that there will be a test problem before the end of the year where I do not give you the mass of the object. Mass doesn't matter. It drops out of your equation, and I guarantee you that about half of you are going to freak out and go, I can't do the problem because Lau didn't give me the mass. Oh, okay. I'm telling you now that I'm going to ask that question. How do I know I'm going to ask that question? Or you're in the tests. All right?
So then you would just solve it doing the gravitational energy times the height?
Yeah, like for this problem that we just had, we had 1/2, the velocity was 16 squared is equal to 9.8 times h. No matter what mass of your object is, h is going to work out to be 13. Whether it's a 35 kilogram sledder, a 50 kilogram sledder, or a 100,000 kilogram sledder, it doesn't matter. Because as this group told us, we would have more energy at the bottom, but we'd have to have more energy at the top, and the ratio is still just changing in the mass.
Okay. So when kinetic energy is equal to gravitational energy, the mass just is irrelevant?
Yep, that's an always statement.